Storing UTF-8 encoded text with strings. We talked about strings in Chapter 4, but we'll look at them in more depth now. New rustaceans commonly get stuck on strings for a combination of three reasons. Rust's propensity for exposing possible errors, strings being more complicated data structure than many programmers give them credit for, and UTF-8. These factors combine in a way that can seem difficult when you're coming from other programming languages. It's useful to discuss strings in the context of collections, because strings are implemented as a collection of bytes, plus some methods to provide useful functionality when those bytes are interpreted as text. In this section, we will talk about the operations on string that every collection type has, such as creating, updating, and reading. We'll also discuss the ways in which string is different from the other collections, namely, how indexing into a string is complicated by the differences between how people and computers interpret string data. What is a string? We'll first define what we mean by the term string. Rust has only one string type in the core language, which is the string slice, stir, that is usually seen in its borrowed form, reference to stir. In Chapter 4, we talked about string slices, which are references to some UTF-8 encoded string data stored elsewhere. String literals, for example, are stored in the program's binary and are therefore string slices. The string type, which is provided by Rust's standard library, rather than coded into the core language, is a growable, mutable, owned UTF-8 encoded string type. When rustaceans refer to strings in Rust, they usually mean the string and the string slice types. In here they refer to the string slice type as reference to string. So usually rustaceans refer to strings and stirs as strings. Although this section is largely about strings, with a capital S, both types are used heavily in Rust's standard library, and both string and string slices are UTF-8 encoded. Rust's standard library also includes a number of other string types, such as OS-string, OS-stir, C-string, and C-stir. Library crates can provide even more options for storing data. See how those names all end in string or stir? They refer to owned and borrowed variants, just like the string and stir types you've seen previously. These string types can store text in different encodings or be represented in memory in a different way. We won't discuss these other string types in this chapter. See their API documentation for more about how to use them and when each is appropriate. Creating a new string. Many of the same operations available with vect are available with string as well, starting with the new function to create a string shown in listing 811. Let mut s equal string : new. This line creates a new empty string called s, which we can then load data into. Often we'll have some initial data that we want to start the string with. For that, we use the toString method, which is available on any type that implements the display trait, as string literals do. Listing 812 shows two examples. Let data equal initial contents. Let s equal data to string. The method also works on a literal directly. Let s equal initial contents to string. This code creates a string containing initial contents. We can also use the function string from to create a string from a string literal. The code in listing 813 is equivalent to the code from listing 812 that uses toString. Let s equal string from initial contents. Okay, let me put that over here as well. Let SSS equal string from more contents. Okay, so I have this creating module, and by the way, this I have it set as let string because when I have mute string, it gives me this warning, and I don't actually know how to make that warning go away. So it's not mutable until I have something to put in it, then I'll make it mutable. Here we have the empty string using the new empty string function. Oh, that's what I called it, right? So this is the new string associated function, and I have it listed as a public function in this module, which is creating.rs, and let's see how well split works when this. Okay, sure. Which is here I am, the book, and let's just do this. Right. So I have my main function, and let's see. Can I add everything? I can. Okay, so this is my main function so far. We've got the obligatory allow unused variables, and I'm sure there's a allow not unnecessarily mutable variables, but I don't know that one. So I have declared the mod creating as a public mod in main, and then I have my functions from the module creating, which is just a different file in the source folder called creating.rs, and here I have called those functions with the parent path syntax. And this is that module. I went ahead and printlned all of my string business. So here I can do crun, which is a shortcut for run, and I'll tell it to be quiet, so it just gives me that. So we have initial contents, next contents, and more contents. Because strings are used for so many things, we can use many different generic APIs for strings, providing us with a lot of options. Some of them can seem redundant, but they all have their place. In this case, string from and toString do the same thing, so which you choose is a matter of style. Remember that strings are UTF-8 encoded, so we can include any properly encoded data in them, as shown in listing 814. Oh yes, I recognize this from maybe the old the book website, or maybe the current one, I don't remember. all of these are valid string values. I wonder what language that is. Our browser doesn't know that one. Updating a string. A string can grow in size, and its contents can change just like the contents of a vec_t. If you push more data into it, period. In addition, you can conveniently use the plus operator or the format macro to concatenate string values. Appending to a string with push stir and push. We can grow a string by using the push stir method to append a string slice, as shown in listing 815. Appending a string slice to a string using the push stir method. Okay, so we're going to need to make one of these mutable, and we'll make this one mutable. Okay, and then I'm not going to save it yet because Rust will tell me that it doesn't need to be mutable. Well, can't read my mind, Rust. So we have SSS, which is our string, and then push stir more. We'll go here and go ahead and take out. No, we won't. Yes, okay, so more contents even. Oh, right, yeah. I've got that :W impulse. Okay, so we will now, yeah. I saw that coming. Sure did. All right. Crun. After these two lines, S will contain foobar. The push stir method takes a string slice because we don't necessarily want to take ownership of the parameter. For example, the code in listing 816 shows that it would be unfortunate if we weren't able to use S2 after appending its contents to S1. So we have let mute S1 string from foo, let S2 equal bar, string 1 push stir S2, print line S2 is bar. Yeah, okay. So let's do this. Let SSSS equal even. Right, so far so good. And then we can change this to, oh right, we don't need that, so we'll say SSSS. And go ahead and put those on both sides, and now we want to say plop another one of these in here. Okay. Oh, uh-oh. Yeah. I gotta watch it with all my comma. No. SSSS. There we go. I should do it. So now it should say Next contents, new line. More contents, new line. Even more contents, even. Let's see what happens. Run Q. Even more contents, even. Yes. If the push stir method took ownership of S2, we wouldn't be able to print its value on the last line. However, this code works as we would expect. The push method takes a single character as a parameter and adds it to the string. Listing 817 shows code that adds the letter /, even though down here we got an L, that's weird, to a string using the push method. Okay, well let's push an exclamation point onto SSS. Yeah, okay. So SSS push, and we'll give it that. You know, I wonder, is there a way to get the spacing how I want it, where I don't have the space before even? Do I want the, oh man, and the space after even? Hey. As a result, this code S will contain lol. Concatenation with the plus operator or the format macro. Often you will want to combine two existing strings. One way is to use the plus operator as shown in listing 818. And I think I'm going to switch to my new empty string function now. Right, so we need to push something into this string. Let's clean this up a little bit. Alright. So we need to push some stuff into our empty string. That means I'm going to let this be mutable, and I'm not going to hit save. Alright. Put some, okay, so I'm going to push. Let's just go ahead and push a character. So I want this business. Forgot. Can I find value push in this scope? Oh, I'm so bad at this. Okay, what is it supposed to look like? Right, I got that backward. Okay, so we want delete to the that thing, and then hey. Okay, so now our S has the exclamation point. Right, so now we're going to let another string, let SS equal bang. So let SS equal, and we will say string from bang. And now, concatenate them. Let SSS equal, we want to go SS first, right? So SS plus a reference to S, to why do they do, so they have S1 plus a reference to S2. Okay, so, well, let's try this. SS plus S, and we'll see what we get. Mismatched types. So one of them should be a reference. Okay. So now we should be able to run this. And oh, I forgot that I want to print it. So we will say print line this and that and one of these and that and SSS. Great. So now we can cronk, bang! The string S3 will contain hello world as a result of this code. The reason S1 is no longer valid after the addition and the reason we used a reference to S2 has to do with the signature of the method that gets called when we use the plus operator. The plus operator uses the add method, and the signature for the add method takes takes self and a reference to stir as arguments, and then outputs a string. This isn't the exact signature. That's okay. That yeah. In the standard library, so okay, the plus operator uses the add method, whose signature looks something like this: function add parameters self and s of type reference to stir return string. This isn't the exact signature that's in the standard library. In the standard library, add is defined using generics. Here, we're looking at the signature of add with concrete type substituted for the generic ones, which is what happens when we call this method with string values. More in chapter 10. This signature gives us the clues we need to understand the tricky bits of the add of the plus operator, which maybe I should call it the add operator. First, S2 has an ampersand, meaning that we're adding a reference of the second string to the first string because of the s parameter in the add function. We can only add a string slice to a string. Do I need to say a reference to string slice? If I say string slice, does it mean reference to stir? I think it does. We can only add a string slice to a string. We can't add two string values together. But wait, the type of reference to S2 is reference to string, not reference to stir, as specified in the second parameter to add. So why does listing 818 compile? The reason we're able to use reference to S2 in the call to add is that the compiler can coerce the reference to string argument into a reference to stir. When we call the add method, Rust uses a AdRef Coercion, which here turns reference to S2 into reference to S2 collection indexing, pretending to be collection slicing. We'll discuss AdRef Coercion in more depth in chapter 15. Because add does not take ownership of the s parameter, S2 will still be a valid string after this operation. Second, we can see in the signature that add takes ownership of self because self does not have an ampersand. This means S1 in listing 818 will be moved into the add call and no longer will be valid after that. So although let S equal S1 plus reference to S2 looks like it will copy both strings and create a new one, this statement actually takes ownership of S1, appends a copy of the contents of S2, and then returns ownership of the result. In other words, it looks like it's making a lot of copies, but it isn't. The implementation is more efficient than copying. If we need to concatenate multiple strings, the behavior of the add operator gets unwieldy. So here we would have let S1 equal string from tick, and then S2 tack, S3 toe, let S equal S1 plus string literal a hyphen plus reference to string 2 plus string literal hyphen plus reference to string 3. At this point, S will be tic-tac-toe. With all the add and quote characters, it's difficult to see what's going on. For more complicated string combining, we can use the format macro. So here we have our S1, 2, and 3 being tic, tac, and toe. Let S equal format macro, and the syntax is just like a print macro. Groovy. This code also sets S to tic-tac-toe. The format macro works in the same way as printline, but instead of printing the output to the screen, it returns a string with the contents. I will try it. So we have this is the thing we're going to change. So we want let SSS equal format macro. Really? Okay. All right. And we want, yeah, one of those and one of those, and we don't need that other stuff. Oh, right. So what is it even saying? Yeah. I mean, I gave it nonsense, of course. So here, and then delete to the end of the line, and that wasn't really what I wanted, but I changed to the end of the line. Okay, this will be, we want SS and then S. So SS, comma, S. This should run just the same. Bang. This code also sets S. I already read that. Did I? The version of the code using format is much easier to read and doesn't take ownership of any of its parameters. I like that. Indexing into strings. In many other programming languages, accessing individual characters in a string by referencing them by index is a valid and common operation. But if you try to access parts of a string using indexing syntax in Rust, you will get an error. Consider the invalid code in listing 819. Here we have let S1 equal string from hello. Let H equal S1 index 0. This code will result in the following error. The trait bound standard string string, standard ops index, that integer, okay, let h equal s, and it says the type standard string cannot be indexed by integer. Okay. The error and the note tell the story. Rust strings don't support indexing. But why not? To answer that question, we need to discuss how Rust stores strings in memory. Internal representation. A string is a wrapper over a vec of U8s. Let's look at some of our properly encoded UTF-8 example strings from listing 814. First, this one. Let len equal string from hola.len. In this case, len will be 4, which means the vector storing the string hola is 4 bytes long. Each of these letters takes 1 byte when encoded in UTF-8. But what about the following line? Note that the string begins with the capital Cyrillic letter Romanized spelling ZE, not going to try to pronounce it, not the Arabic number 3. Let len equal string from a long Cyrillic word, .len. Asked how long the string is, you might say 12, but Rust's answer is 24. That's the number of bytes it takes to encode all of that into UTF-8 because each Unicode scalar value in that string takes 2 bytes of storage. So an index into the string's bytes will not always correlate to a valid Unicode scalar value. To demonstrate this, consider this invalid Rust code. Let hello equal hello, I presume in Russian or some other language that uses Cyrillic. Let answer equal reference to hello index 0. What should the value of answer be? Should it be 3, the first letter? Oh, that's not 3, that's the Cyrillic letter spelled Romanized ZE. Should it be that, the first letter? When encoded in UTF-8, the first byte of that is 208 and the second is 151. So answer should in fact be 208. But 208 is not a valid character on its own. Returning 208 is likely not what a user would want if they asked for the first letter of this string, but that's the only data that Rust has at byte index 0. Users generally don't want the byte value returned even if the string contains only Latin letters. If reference to string slice hello index 0 were valid code that returned the byte value, it would return 104, not H. To avoid returning an unexpected value and causing bugs that might not be discovered right away, Rust doesn't compile this code at all and prevents misunderstanding early in the development process. Bytes and scalar values and grapheme clusters, oh my! Another point about UTF-8 is that there are exactly 3 relevant ways to look at strings from Rust's perspective, as bytes, scalar values, and grapheme clusters. That's the closest thing to what we will call letters. If we look at this Hindi word, written in the Devanagari script, it is stored as a vector of U8 values that looks like this. It's a bunch of numbers. That's 18 bytes and is how computers ultimately store this data. If we look at them as Unicode scalar values, which are what Rust's char type is, those bytes look like this. And here we have, so we have characters, and the fourth one is, and the sixth one are diacritics. There are 6 char values here, but the fourth and sixth are not letters, they're diacritics. They don't make sense on their own. Finally, if we look at them as grapheme clusters, we'd get what a person would call the 4 letters that make up the Hindi word, that word. Probably means hello. Rust provides different ways of interpreting the raw string data that computers store, so that each program can choose the interpretation it needs, no matter what human language the data is in. A final reason Rust doesn't allow us to index into a string to get a character is that indexing operations are expected to always take constant time big O, a capital O, 1, I don't know what that is. But it isn't possible to guarantee that performance with a string, because Rust would have to walk through the contents from the beginning to the index to determine how many valid characters there were. Slicing strings. Indexing into a string is often a bad idea because it's not clear what the return type of the string indexing operation should be. A byte value, a character, a grapheme cluster, or a string slice. So Rust asks you to be more specific if you really need to use indices to create string slices. To be more specific in your indexing and indicate that you want a string slice, rather than indexing using the indexer operator, which is 2 square brackets, with a single number, you can use that operator with a range to create a string slice containing particular bytes. So back to our Cyrillic example, let hello equal a long word with Cyrillic characters. Let s equal a reference to hello, and then we have a range 0.4. We don't need that 0. Here s will be a string slice that contains the first 4 bytes of the string. Earlier we mentioned that each of these characters was 2 bytes, which means s will be those first 2 characters. What would happen if we used reference to hello with a range from 0 to 1? The answer, Rust would panic at runtime in the same way as if an invalid index were accessed in a vector. Thread main panicked at byte index 1 is not a character boundary. It is inside the first character there. You should use ranges to create string slices with caution, because doing so can crash your program. Methods for iterating over strings. Fortunately, you can access elements in a string in other ways. If you need to perform operations on individual Unicode scalar values, the best way to do so is to use the chars method. Calling chars on this Hindi word separates out and returns 6 values of type char, and you can iterate over the result to access each element. Yeah, now this is happening. Okay, so let's have a new function we will call this pub fun Hindi, and do that. There we are. And I am gonna just copy and paste this. Copy and paste. Wonderful. Oop. Looking good. And now we need to get into main. Great. So let's get out of this and main, and then do this. Creating Hindi. Oops. Oh, because I'm in the comment, right? Okay, so now we want to decomment this, and I'll do it this way: visual over 1, change 2 spaces. I misspelled creating, and now run some Hindi, y'all. Huh. It didn't separate the diacritics, did it? 1, 2, 3, 4, 5, 6, and here I've got 1, 2, 3, 4, and I guess it combined the diacritics. I wonder if that's a change. Okay. The bytes method, excuse me, returns each raw byte, which might be appropriate for your domain. Okay. Well, let's have another one, and we'll call this creating, come on now, Hindi bytes. That's fine. And we will creating. Yes, I'm aware. Okay, and now we'll say